monomials, we are going to be basically looking at fraction-style monomials. So remember, of course, we could show division side by side with the division sign, but another way to show division, for example, 15 divided by 21, is to just show it as a fraction, and that's how you're going to be seeing them today. So this is division, just looking at it like a fraction. Because we can look at it like a fraction, we are going to simplify it like a fraction. Now, by now, I think you guys are all pretty strong at simplifying fractions, but let me kind of go back here, and on this fraction, let me show you why it works the way that you guys are so used to doing it. What we want to do is find a common factor that we can divide them both by, is sort of how we've been doing it. Another way to think about it is to list the pairs of factors. If you think we just did factors yesterday, there's 1 and 15, but those aren't in common with the 21. So 3 and 5, and 3 times 7 for the 21. So the common factor that you guys would have come up with was 3, because they do both divide by 3. But I'm showing you this way because this is sort of how we're going to be doing it once we throw the variables in. If I have 3 over 3, let's say I separate this into two separate pieces, 3 over 3 times 5 over 7. Anytime, oh, there goes my pen. Anytime we have a numerator and a denominator that have the same value, what does that equal? Diego? 1. So this 1 times what's left, 1 times 5/7 is just 5/7. You can also think of this as when the numerator and the denominator are the same, and it's being multiplied like we have here, you can cancel them out because they make 1. And we're taking the 1 times whatever's left, which won't change it. Now, if this were just a regular fraction, you wouldn't have to, I'm not going to make you show it this way on a regular fraction. You can do what we've always done, which is, oh, they both have a common factor of 3. If I divide both these numbers by 3, I get 5/7. You're welcome to do that for any regular number of fractions that you see. But I wanted to show you this pattern here, because that's how we're going to be solving the ones that have variables. So let me start with one with variables so I can show you what I mean. Negative 4xy over 10x. If I wanted to simplify the instructions that you have for the homework today, we'll just say simplify. We're going to simplify it like we would a regular fraction by finding a common factor. So first of all, 4 and 10. We'll ignore the negative for now. 4 and 10 have a common factor, Carissa. 2. Now, is there anything else that both the numerator and the denominator have in common? Brian? An x. So let's take that as part of the factor. Now, again, I'm going to show you this way to do it, and then on the next problem I'll show you yet another way to think about it. 2x, well, how would I get, if that was one factor of this, how would I get the rest of it in there? Well, the 2 must be multiplied by negative 2 to make negative 4. I've already got the x, so this one must also have a y on it. If I multiply these, 2x times negative 2y, I get negative 4xy. Okay, so again, this way might be complicated. If you don't like this, you can switch when I show you the next method. But this is just, I'm trying to show you that the factors are what we're looking for. Common factors. Okay, 10x, I've already taken out the 2x. What would I have to multiply this by to get it to be the original of 10x, Jim? Times 5. Now think about what we did on the last one. Anytime I have the same numerator and denominator, since it equals 1, 1 times this is just going to equal this. One way to think about that is that we can cancel them out, and so my answer is what's left over when I've gotten rid of that 1 that was made by the same factor in the numerator and the denominator. So one of the things you can try to do for this is to try to pull out that factor and then see, well, what else would I be multiplying by? Questions on this one? Let me show you one more method It's, again, just another way to think about this style of problem. Let's make it a little bit harder. 35, hold on. I'm just going to say x. Sorry, we're going to get to the exponents later. 35x divided by 42x. So ignore that blob. I was going to do an exponent, but we got to first cover some exponent stuff. Now, we could come and do the same thing. We could say they both have an x. That's a common factor. They both have a fact. What other common factor? Maybe the greatest one. Izzy? 7. Okay. Now, another way you can solve these, if you don't want to write it out like I did here with the factors, is just to know that whatever's going to be the same in the numerator and the denominator, we're going to end up canceling it out. So right away, I see x and x. That's the same. Those are going to cancel out. And 35 and 42, we could write the factors, or we could just solve it the way we would a regular fraction and deal with the number part the same way you guys have been simplifying fractions for years now, by dividing them both by that common factor. 35 divided by 7 leaves 5, 42 divided by 7 leaves 6, and the x is canceled out because there was 1 in the numerator and 1 in the denominator, and that would equal 1. And 1 times 5/6 is just 5/6. So rather than, if you don't want to write the factors out like we did here in this orange example, just know that you can just cancel whatever's the same in the numerator and denominator. Now notice, this is very important, this is only for monomials. There's no addition or subtraction happening here. We don't have binomials. You cannot cancel things like this when you have binomials, and we'll get to that later in the chapter. Okay. An exponent rule I need to show you. Exponent rules. We've had a few of these using the A and the M and the N. If we divide the same base, right, A being our base number, division like we're working on, you have to see the base in both the numerator and the denominator like we have here. If you are dividing the same base, you subtract the exponents. For example, x to the 7th over x to the 3rd. If I follow this pattern, what would my answer be? Kate? Which equals 4. You could write the 7 minus 3 first if you want, but what I want you to get to is the final answer of 7 minus 3, which in this case, of course, is 4. Now, let me show you a second one like this and another way to think about this, because we're going to be seeing a lot of these exponents coming up. What if I said b cubed minus b squared? Well, we could use this rule and we would get b to the power of 1, right? 3 minus 2 makes 1. Another way to think about this is that this means b times itself 3 times, right? And the bottom one, well, that means b times itself twice. Let's think about what I just did up here. Let me scoot it down for just a second. In the blue, was I canceled things that were the same in the numerator and the denominator. If you want to visualize this as 3 b's being multiplied and 2, let's see what we could cancel. You have to cancel the same in the numerator and the denominator. So I could go 1b and 1b. I could get rid of 1 more b in the numerator and 1 more b in the denominator. I cannot cancel out this third b because there is not a matching 1. So what am I left with? 1b. Now, the exponent rule says 3 minus 2 equals to the power of 1. Here's the power of 1. If all you have is the variables like this, I'd say just use the exponent rule, just subtract the exponents. But here's where this method is going to be very handy. Next problem. I'm going to kick it up a notch now. I'm going to go back to the one I started to write with the exponent. 35 x cubed y squared. There's a monomial. Divided by 56 x to the 5th yz. Now we could write out all the factors, or we can just start to cancel. We can only cancel numerators and denominators because this is all multiplication. If there was a binomial with a single addition or subtraction sign, we couldn't do this. Let's start with the numbers, just like we would a regular fraction. 35 and 56 both have a common factor that we could divide out of, Vincent? 7. If I divide both of those by 7, what's left? 5 and 8. Now, let's think about what I was just saying about canceling variables. If I have x cubed here, now again, you don't need to write all this unless you want to. That means x times itself 3 times. If I have x to the 5th in the denominator, that means x times itself 5 times. How many am I going to be able to cancel out from the top and the bottom? It has to be this. You have to do the same thing to the numerator that you do to the denominator. How many? Izzy? Okay, good. I could do 1, 1, 1, 1, 1, 1. I can cross out those 3, like Izzy just said, or some of you were holding up your fingers. Now, the 2 that are left, notice where they are left over. I'm sorry, that yellow doesn't show up very well. The leftovers are where? Numerator or denominator? Pammy? They're left in the denominator. How many of them? 2. So you just have to pay attention, where are the leftovers? Now you don't have to write these out. You could, many of you, look at this x cubed and x to the 5th and say, okay, what's the maximum I can cancel from both? I can get rid of 3 from here. That means they're all gone. If I get rid of 3 from here, well, there's still 2 left. Let's try it on the y's. Y squared and y. Without me writing it out, how many can I cancel from top and bottom if it has to be the same amount? Luke. Okay, good. There's only 1 in the denominator, so I can get rid of that 1. If I get rid of 1 also from the numerator, how many are left? If it was y squared and I got rid of 1, Leanna?
1.
There's 1 left. And where is that extra 1? It's in the numerator. Because the y squared was in the numerator. So my leftover 1 that I can't cancel is up here. What about the z? Can I cancel it? Nope, there's no other z's. It doesn't change. It stays where it is. Should we do another one that's like that?
Yes.
No, you guys are too smart. You don't need it. All right.